All right, so good afternoon. How are you doing today? Good? Okay. So I think Ray gave a pretty good introduction on what Kubernetes can do in terms of autoscaling. I'm going to do exactly opposite. I'm going to destroy pods and nodes, and we are going to see that in a demo. All right? For those who have been using Kubernetes a lot, it might look like a very trivial thing, but for those who are about to start with Kubernetes, this would be a good starting point and a good introduction. Originally, I planned this as a 2-hour workshop, but clearly that's not happening. So what I've done is that I'm going to give you an introduction here, and I have compiled some text on how to set up your own Kubernetes lab, how to write basic applications, basic pods, replication controllers, and everything. And I have created a bunch of examples. I'm going to share all the URLs with you in the end of the talk. Sounds good? All right. So we shall start. By the way, my name is Aditya. Hello. I am a consultant and trainer for Docker, DevOps, configuration management, whatever comes in my way. I have been a contributor to Fedora project, cloud efforts, infrastructure efforts since quite some time now. So yeah, that's about me. So what we are going to discuss today is that we are going to figure out what kind of problem we are trying to solve with Kubernetes here. We are going to look at the Kubernetes components, assembly pods, replication controls a little bit more in detail than what Ray did. And then we are going to understand the architecture of how different components of Kubernetes actually talk with each other. And lastly, the demo, of course. So yeah, my basic use case is that I want my services to run, right? I don't care how they run, what kind of disasters they have to go through. That's not my problem. My problem is to ensure that whatever my application is, it always runs. That's what we are trying to do, right? All right. So the basic entities in Kubernetes world, these are pods. Pods are the smallest indivisible entity in Kubernetes world. That means that you cannot divide a pod further, right? Pod is made up of, okay, let's go there later. The next entity is a replication controller. So replication controller can consist of multiple pods. The whole idea behind a replication controller is to make sure that you can scale your pods as and when required, and they do not go down very often. Or if they go down, there are mitigation steps involved. Services and endpoints. Services and endpoints creates an abstraction around the replication controllers so that you can access your pods. Right. So a pod, as in a pod of peas, a pod can consist of multiple containers. And within a pod, it is possible to mount external drives. So for example, if you want to have a pod of MySQL and you want to have your data somewhere outside, say in Gluster or something like that, then it's possible to mount a Gluster drive on a node, and then you can have a pod mount an external Gluster drive there, right? So that way your data remains persistent and not dependent on the life cycle of the pod itself. Container to container network is transparent in the sense that if you have two containers running inside a pod, then those containers can talk to each other as localhost. So if there is a port 8080 open on container 1 and port 9090 open on container 2, then they can access each other via localhost interface. Am I going through right? All right. Replication controller is basically a collection of pods, and they are designed to be highly available. And that's what we are going to check out today, that what happens if we bring down a container pod by force. Yeah, so essentially they try to do everything. Replication controller is the most powerful entity inside the Kubernetes world. And yeah, and services and endpoints. Basically, they try to facilitate the communication between a real world entity like me and between a Kubernetes entity like a replication controller and pods running inside it. So if I have to access a pod running inside a replication controller inside a node, instead of binding the ports, which is not a very good way, we should ideally create a service around it, and we should access those pods via services. So they abstract a lot of routing, a lot of networking nitty-gritties inside it. So how this all happens? Right, so what exactly happens is that we have two components here. One is Kubernetes master and another one is Kubernetes node. Now master runs a controller manager, scheduler and API server. API server is what Ray was just using to do scaling and all. API server basically exposes a REST API. Scheduler decides that on what node, if you are running a multi-node environment, then scheduler will be responsible for picking up the node and telling them that, okay, this node has this much resource available and probably we should run the next pod here. Controller manager basically runs a lot of, it manages a lot of controllers like replication controller, service controller, so on and so forth. So it's the brains. Now node runs a kubelet and kubeproxy. Kubelet is the guy who does the entire work for us. Kubelet is going to run the actual pod and the containers. Kubeproxy is responsible for the routing, like I just told you that we need services to access these Kubernetes pods. Kubeproxy will create IP tables rules, and via that we'll be able to access our services running inside the nodes. And pods, obviously pods will be scheduled to run inside a node. Okay, right. So let's start with a demo. Is this should be visible, right? All right. So let's check out how. Okay, so I'm not going to show you pod. I'm directly jumping to replication controller because a replication controller is actually a collection of pods. So basically, we'll be running pods using a replication controller. Let me just show you how the definition looks like. Oh, okay, too much. Right. So it's a simple YAML file. And yeah, so we have defined the, inside the spec, we have defined the pod configuration here that I need a Nginx Flask pod. That's the name of the pod. And the pod will consist of two containers. Container number one is Nginx PP 5000. Basically, it's Nginx doing a proxy pass to port 5000. And the second one is the demo app. Demo app is a Flask app. What you can do inside the app, what you are doing is just serving out a web page and image and all those regular things. So these two containers, I'm going to run in a pod inside a replication controller. Any questions so far? Am I going too fast, too slow? Okay. Okay. I will also show you the service configuration. Yeah. So service configuration, basically, I'm going to select Nginx Flask pod, and I'm going to run the service for that particular selector, such that the target port, which is the port of the container, is 80, and it's going to expose the service on port 80 as well, right? Sounds good? All right, let's run it. Okay, I can't find my mouse. Does anybody know where is my mouse? Yeah. First off, let's see if there is anything else running here. Nope, this one is empty. and this one is empty as well. All right. Right, so we have created the replication controller. Let's see, okay. The replication controller is running. Let's check out if our pods are booted or not. Not yet, they are in pending state. In the meantime, what we can do is, we are going to create the service for it. All right. Okay. Let's see if our pods are up or not. Okay, one of them is up. All right. Okay. What's going on? Yep. Okay. Both of them are up now. So now we expose the pods via service. So if you see, there is a service Nginx Flask service there, and it has an IP 10.10.1.2.3.6, and it's listening on port 80. So basically, instead of accessing my applications or my pods via direct IP to the node, Kubernetes is going to create an endpoint where I can hit, and it will be dynamically routed to any of the healthy pods. Right? So if I would have had 10 pods here, this will act like a load balancer for me. Of course, in environments like Google Cloud, there will be an actual load balancer. But if you're running in a private cloud or for small setup where you do not want a load balancer or you cannot afford a load balancer, you can go with this technique. So let me just take this IP address. And wait. Okay, yeah. So this application, this particular page is being served by our Nginx Flask application. Now, what we want to actually see here is what happens if we kill a particular container. So let's pick one particular machine, let's say like this one. We do Docker PS here. Okay, which one of the containers you do not like? Let's pick the first one. Just going to kill it. All right. Die. All right, it died. Okay, so ideally, this should affect the application, right? Where is my browser? Yeah. And let me refresh it. See? All right, nothing is happening if I refresh. So the fault tolerance here is that even if my pod, which was Nginx, which was serving the page, it went down, but the downtime which I saw was nil. So even if I keep on refreshing this, it will still work. And let's see, and if you see here again, 35 seconds ago, basically Kubernetes booted up a replacement. So in terms of pod, if your pods or if your individual containers, your applications crashes in production, this is a lifesaver. Your viewers, your customers will see almost negligible impact. Of course, if it's a very high traffic website, then there might still be a couple of seconds of 503s or 502s depending upon your application. But otherwise, this is a pretty good solution. Now, let's take it to another level. How about if I kill a node itself? That would be interesting, right? So let's go to this guy. So these are my node 1, node 2. I don't like this node, let's kill it. Boom. Okay, and let me go to my browser. Now, works? Okay, what really happened? Wow, no downtime. Okay, so both of them got rescheduled. There was one restart here. And if you go ahead, you see that there was no restart previously. So what exactly happened was that that particular pod, we ran 2 replicas, right, in our configuration. The first one actually died and it got restarted and rescheduled here. So if we check out, damn. Okay, so if we check out Docker PS here now, okay, the second one has not started. Interesting. Let's see. It's dead, right? Yeah, it's dead. Okay, that is very interesting. So ideally there should have been a replacement pod here, which I'm not seeing right now. Let's give it a minute or so. In the meantime, yeah, do you guys have any questions around scaling, fault tolerance, around Kubernetes in general? Yep. Can you please repeat that?
The IP address if you used access to service, where was that? What was that IP address of?
All right. So networking in Docker and Kubernetes world is a very big mess. All right. Sorry. So the question was that where did I got the IP address from? Right? Yeah. So what happens in a cloud environment? Those IP addresses are usually routable. They are, for example, if you go to Google Cloud, what they'll do is they'll give you a chunk of IP address, and that will be routable. But for the purpose of demo of a private setups, what you need to do is you have to take a chunk of IP address which is routable, and you have to manage those routes. Okay. So there are 2 tricks to it. There are 2 steps to the entire trick. First one is that when you do the Docker setup, and when Docker creates the bridge, before creating that bridge, you actually have to give the bridge IP address. It's by default it's 172 something. So I've changed that to 10.10.1 in one of them, and 20.1 in another one of them. And what I've done here on my master is a very neat trick actually. I have injected these 2 routes. If you can see these 2 routes. So now those 2 routes are in my routing table. The entire 10.10. series becomes routable, and my master knows where are these guys lying out.
But you need this route on the nodes also if you want to use internal DNS. Do you use Flannel or something like that?
We can use, yeah, you can use Flannel. You can use Flannel. I'm not using Flannel. This is a very basic setup, but you can use Flannel at all. Yeah, so Flannel, Weave.
You need probably the routes only also on the node, because if you try to so that host each other, if you have some services, internal services, so that they can reach each other, use Sky DNS, something like that. So
Yes. Yeah, if your pods need to talk to each other, then yes, you would need, you would need that. Yep.
What happens with the Kubernetes cluster if the master dies?
What happens to the cluster if the master dies, right? So this demo is only with one master. Ideally, you will go with a master cluster. So, so in the background, there's etcd running, and all the masters talk to etcd continuously, and they know which one is the primary master at the moment. And if that master dies, a new master will take its place.
Is there an impact in terms of latency on the core process of the pods? The process of fault tolerance that is.
Okay, so if I understand the correct question right, you're asking, are there latency impacts, or in the sense, are there delays when a pod dies? Yes, there is a delay. but the delay is usually of the order of milliseconds, which is very small. That said, if your website is already heavily loaded, and at that point if something dies, there will be a few customers complaining, but the recovery will be pretty fast. I mean, it will be in the order of 1 or 2 seconds max. But yeah, for those 1 or 2 seconds, there might be some customers who might go to an unhealthy pod and they will complain. Anything else? Yep.
The fault tolerance of the pods out of the box. We need to do something.
Pods are not fault tolerant. Pods can die anytime. Replication controller is what makes it fault tolerant. So replication controller basically is a watchdog. It keeps an eye on the pods, and if a pod dies, it replaces it creates a replacement. Oh wait. Yep. Now it has booted the replacement container. So it took like I think quite some time, which should not have happened. But at least it stopped routing to the bad one. Yep.
Just to clarify,
Mhm.
are pods becoming fault tolerant just by virtue of running an application controller, or do you need to do a lot of additional configuration?
So for stateless application like HTTP is pretty much stateless, right? Or whatever, or if your storage is somewhere external like Gluster or something like that. In those cases, replication controller are very good way to go. Pods are not fault tolerant. Let me be very clear. Pods are not fault tolerant by themselves. It's the replication controller which keeps an eye on them and makes sure that if a pod dies, it boots up a replacement. And if, for example, your application is not session dependent or not, it's not a stateful application basically, then it is the way to go. You will have like a very good uptime using this strategy. For stateful applications, you might have to think of a few more tricks, I guess. Yep.
Does the replication controller span the pods on multiple physical hosts?
Okay. So replication controller is actually not a thing running on all the hosts. Replication controller basically, so this diagram which we just saw, where is the diagram? Yeah, so in this diagram, basically controller manager is the guy who is managing all the replication controller, service controller and everything. So these guys, what they do is that they keep on talking to Kubelet via API server, that what is the current state, and when they realize that one of the container has died or one of the pod is not healthy, then they will boot a replacement. Yep.
How does it detect if the Cube API server has issues? Because that seems like a simple question.
How to detect if Cube API server has issues?
Yeah.
Yeah, so as I said, so basically you in production like environment, you will never go with a single master. You will have multiple of them running.
I understand, but do they detect themselves if there are issues?
Yes, so not inside the picture is actually a etcd server running. etcd running, which is not in the diagram, I should add that. So what happens is that etcd server maintains a list of current masters and which one is the primary one. And if there are any problems, then another master is selected and the bad one is removed. etcd itself is fault tolerant in the term of distributed. Anything else? All right. So I have, as I said, that this was supposed to be a workshop where we would have done things hands-on. So I have taken a liberty to jot down certain points for you. One thing. So this has all the examples, all the diagrams, all the simple and complicated examples as well. So feel free to have a note of this and download it. Sure. Go ahead.
When they start development of Kubernetes,
It was? Salt stack, salt stack. Yeah, I don't know. No, I don't know. Thank you.